So this is the second session for us in friction. So in the previous class we have understood about the two types of friction, static and kinetic. Okay, and we have understood about the fact that static friction it acts in such a way that it balances the tangential force, the tangential external force to prevent the tendency to slip. Okay, so it basically acts where there is no slipping occurring, but friction is the one that is preventing the object from slipping on the surface. Otherwise there would be, but for friction there would actually be slipping. So the magnitude of static friction can be anything from 0 up to a certain limiting value, which is the coefficient of static friction multiplied by normal reaction. Okay, whereas kinetic friction is the type of friction that acts when there is actually slipping taking place. Okay, and it is independent of the external tangential force. It will act whether or not there is any external tangential force, and its magnitude will be independent of the tangential force. It will act as long as the surfaces in concern are in a state of slipping with respect to each other, or they are in a state of relative motion in the tangential direction. So kinetic friction acts, okay, in such a way that it opposes slipping. Okay. Its magnitude is independent of external force. I mean tangential external force. Of course, its magnitude will be affected by normal external force because normal reaction will be affected by. Okay, so kinetic friction has a fixed magnitude, which is coefficient of kinetic friction multiplied by normal reaction. Okay, and its direction always opposes the direction of slipping. So we have understood this in context of all the examples last time. So let's start with some more examples today. So we will start with the very important example of the inclined plane problem. Okay. So friction on an inclined plane. So let us say we have a rough inclined plane which is inclined at some theta to the horizontal. Okay. And this surface has coefficient of static friction equal to 0.7 and coefficient of kinetic friction equal to 0.6. Okay. And we place some block gently on the surface initially at rest. So block, okay, is placed gently at rest on a rough inclined plane. Okay. Find its acceleration, if any, and the frictional force acting on it. if in the first situation theta is equal to 30 degrees, and in the second situation theta is changed from 30 to 37, but the coefficients of friction are all the same. Okay, so just try this out. So first of all, you have to understand whether the block is going to remain at rest in equilibrium or is going to slide down the inclined plane. So for that, you have to understand two things: what is the limiting static friction available, and what is the tangential force down the inclined plane, okay, which is trying to make it slip. If the tangential force down the inclined plane exceeds the limiting friction, then it's going to slip, whereas otherwise it is going to remain at rest in static position. So start with the free body diagram of the block, okay, and try to understand these two things. Make the free body diagram, okay, analyze the limiting friction available, okay. So in this case the tangential force will be mg sine theta, okay. And the limiting friction obviously is coefficient of static friction into normal reaction. So whichever dominates, that one wins. Okay, if limiting friction is greater than tangential force, then friction wins, so the object remains at rest. If the tangential force exceeds, then that one wins, and friction is not able to prevent it from slipping down the inclined plane. So hope all of you understood the question now. Okay, anybody got it? In which case, the first case, Samarth, uh, yeah, Aditya, your answer is correct. Samarth, your answer is not correct. You have to check once more. Yes, Viraj, your answer is correct. Vaishnavi, correct. Okay, so let's analyze this. So I'm going to show the weight in a resolved form. So mg sine theta, whatever the mass, we can substitute the values later, and mg cos theta. These are the components normal to the inclined surface and tangential to the inclined surface. This angle is theta. So anyway, so normal reaction, you know, is equal to mg cos theta. That is not affected by friction. Now friction is going to act in this direction. So you can see that limiting friction, that is the maximum static friction available, that is given by the expression mu s into normal reaction. Okay. Therefore, for equilibrium, that is to remain at rest, what is the condition that mg sine theta should be balanced by static friction, and static friction cannot exceed limiting value. So that means the condition is that mg sine theta should be less than equal to this value. That means mg sine theta should be less than equal to mu s into mg cos theta. Okay. So that means the coefficient of static friction should be greater than equal to tan theta. So this is the condition for equilibrium in this case. Okay. And if this condition is satisfied, and in this case what will happen is that static friction will balance mg sine theta. Okay. Whereas on the other hand, if mu s is less than tan theta, okay, then we can say that slipping will occur. Okay. Because this condition, it will imply that mg sine theta is becoming greater than limiting friction. Okay, so slipping will occur. So if slipping occurs, then in my free body diagram, there is acceleration like this. And the type of friction acting is kinetic friction. So it is mu k into normal reaction. So in this case, if slipping occurs, what will happen is that mg sine theta minus kinetic friction will become mass into acceleration. And normal reaction is equal to mg cos theta. So we'll substitute this in this equation and we will get mg sine theta minus coefficient of kinetic friction into mg cos theta is equal to ma. So the acceleration will become g into sine theta minus mu k into cos theta. So we can develop this concept beforehand, and now we can substitute the values and understand which of the two cases is occurring. So just go through this analysis once, then I will explain to you how to apply the values over here. This would be the case where if static friction is acting, how it would look for equilibrium. So Viraj, your answer for the second case is not correct. Devansh, your answer is correct. Vaishnavi, you also check your answer. And Devansh, check the magnitude of friction in the first case. Yes, that's correct now. So see, the way I have set up the question now, we can actually directly compare the values of coefficient of static friction against tan theta, and we can see which of the two cases will take place. If coefficient of static friction is greater than equal to tan theta, then it is equilibrium. If mu s is less than tan theta, then it is a case of slipping. Okay. So in the first case, yes, that's correct now, Devansh. So what is happening here is in first case, theta is equal to 30 degrees and coefficient of static friction is zero point 0.7. So you can see that tan theta is 1 by root 3. So you can write as root 3 by 3, approximate that as 1.73 by 3. So that is approximately 4 something. Okay. So we can clearly see that coefficient of static friction is greater than tan theta. So what this means, this is the equilibrium condition. Because this basically means that my mg sine theta is going to be less than limiting friction. So my free body diagram will look like this. The acceleration of the block will be zero. The type of friction acting will be static friction. So it will be balancing the tangential force. So this will be my, so static friction will balance mg sine theta. So in this case, static friction will be equal to, how much was the weight? 100 newtons, right? M was 10 kgs, I think, and we'll take G as 10, right? So the magnitude of static friction acting will only be 50 newtons. The limiting value is more. The limiting value of static friction available is mu s into n, that is mu s into mg cos theta. So it is in fact equal to 0.7 into 100 into root 3 by 2. which is quite a bit more. It is more than 60 newtons. So maximum friction available is more than 50 newtons, but that much friction will not be acting. Only 50 newtons will be acting, because what is friction's job here? It is to block the mg sine theta. It should not exceed mg sine theta, because otherwise the block would be accelerating in the upward direction. So the amount of friction acting in the first case will only be this much, even though the maximum friction available is up to this much. And obviously it will be in equilibrium. So the acceleration will be zero. Yeah, Shikhar, look at the free body diagram and understand the condition for equilibrium. Forces have to balance. So I'll again show you the condition for equilibrium here. The condition for equilibrium is developed over here. That mu should be greater than tan theta, greater than equal to. Because on the other hand, if mu is less than tan theta, then slipping will occur. Okay. So if it's in equilibrium, static friction balances mg sine theta. Okay. Whereas if it is in a condition of slipping, then the friction acting is kinetic friction. It's kinetic friction that acts. So that is mu k into mg cos theta. So we get finally the acceleration equal to this much. So an example of slipping for us here would be the second case. The second case, you can see that because I've taken my theta more now, it is 37 degrees. Okay. And coefficient of static friction is still the same, 0.7. Okay. So you can see that tan theta is 0.75. Tan 37 is 3 by 4. So you can see that tan theta is greater than coefficient of static friction. So this is the condition for slipping, because our mg sine theta is becoming greater than mus into normal reaction. So now it's going to look like this. It's going to accelerate down the inclined plane, because static friction is not able to balance mg sine theta. So mg sine theta is dominating. This is what is okay. Okay. So the acceleration will directly be g into sine theta minus mu k cos theta. Okay. So where we get this from? We get this from the fact that mg sine theta minus kinetic friction is the net force along the inclined plane, and kinetic friction will be equal to mu k into normal reaction, that is mu k into mg cos theta. Substitute that, and from that you get this. So the acceleration will become 10 into sine 37, that is 3 by 5, minus zero point 0.6 into cos 37, that is 4 by 5. So you can see that acceleration is 10 into 0.6 minus zero point 0.6 into zero point 0.8 meters per second square. So this will be the acceleration, and the friction acting will be kinetic friction. So that will be zero point 0.6 into 100 into 4 by 5. So 48 newtons. This will be the amount of friction acting. Okay. So this is the complete explanation of the second part. The acceleration should come out to be 1.2 meters per second square, and you should be getting the amount of friction acting, the magnitude of friction acting as 48 newtons. Okay, so hope all the parts of this question, both the parts are clear. Let's move on to another one. So we have a fixed ceiling here. And we have a block attached over here, another block over here. So this surface has a coefficient of friction as 0.4. So basically what it means here is the coefficient of static friction is equal to the coefficient of kinetic friction, equal to mu. Okay. And this block is M1, this block is M2. So take G as 10 meters per second square, and M2 is, or let's say M1 is given to us instead of M2. M1 is 50 kilograms. So in the first part, we have to find the maximum value of M2 if the system remains in equilibrium. Okay, when released with the thread top. And secondly, if M2 is instead of this maximum value, if M2 is equal to if M2 is equal to 60 kilograms, then find the accelerations, if any. Yeah, the pulleys are standard pulleys, and okay, so thread is also a standard type of thread. So all those things are there. Okay, okay, just try out this question. So as always with anything else, this is also a problem of free body diagram. Make the FBD of M1 and M2 and try to understand for the first part that if they are in equilibrium, how the forces are balancing, and how in order to balance the forces in case of M1 we need static friction. And what is the maximum static friction available to us, that you can check out. Okay, so let me confirm the answers. So you can obviously see the condition for equilibrium. What we want is that for the block M1, this tension should get balanced by static friction. Okay. But then the question is how much static friction is available to us? And the answer to that is coefficient of friction into weight. Okay. So for equilibrium, tension should be balanced by static friction. Normal reaction is equal to the weight. So that we have taken as 500 newtons. Right? 50 kg was the mass. Yeah. Okay. And coefficient of friction is mu is equal to 0.4. So that means the static friction is less than equal to mu n. So static friction is less than equal to 200 newtons. Okay. So this is the limiting condition. This here, it is called the limiting condition. So from equation 1, you can see that tension, so tension should not exceed 200 newtons. Okay. And for that, we can understand the weight of the block should not be more than 100 newtons, the weight of the other block. Because on M2, you can see that there's a total of 2T. So the condition for its acceleration to be 0 is that 2T balances M2G. So T is equal to half its weight. So now substitute this condition here. So M2G should be less than equal to 400. That means M2 should be less than equal to 40 kg. So this is the limiting condition. This is the equilibrium condition. So this will give you the answer for the first part. Right. So hope this is clear to all of you. Yeah. I'll confirm the values for the second one. Okay. So obviously if the mass of the second M2 is more than 40 kg, there's going to be acceleration. So that's where our second part comes in. The second part, M2 has been taken as 60 kg, right? Okay, Ranak, I'll take you back to the inequality. Just go through it, you'll understand. There's nothing big about this, yeah. You just know this condition. Static friction is less than equal to maximum value of it. So what is the maximum value of it? It is mu n. So that is how much? That is in this case 200 newtons. So static friction should be less than equal to 200 newtons. This is the inequality used. The rest is all substitution. Got it now? So friction 200 newton से ज़्यादा नहीं हो सकता है. So tension should not be more than 200 newtons. So if the tension is not more than 200 newtons, then M2G should not be more than 400 newtons, because 2T is balancing it. So there you are. So now in the second case, M2 is taken as 60 kg. Yeah. Rest of the things are same. So obviously in this case slipping will occur. Now you have to understand all the constraint relation and everything. So first of all, you have to understand here that on this block T is acting. So if it has a velocity v at any point of time, v1 at any point of time, the power delivered by tension is plus T v1 here, and here it is minus 2T v2. So this should be 0. This is our virtual power equation. Okay. So v1 has to be twice of v2. So a1 has to be twice of v2. Okay. There's one free body diagram, and the other one, and everything is in inertial frame. Okay. So we have, this is our first equation, T minus mu m1g is equal to m1 a1. Okay, which we can write like this: T minus mu m1g is equal to 2m1a. Okay, because let us say, okay, and m2g minus 2t. Okay. So 2t minus m2g is equal to m2 into a. That is our third equation. Okay. So now multiply this whole equation by 2 and add it with this. Sorry, should be the other way around. Okay. So on doing that operation, 2t will cancel out and we'll get m2 minus 2 mu1, this is equal to m2 plus 4m1 into a. So we'll get the magnitude of a as 60 minus 2 into zero point 0.4 to 50 divided by 60 plus 2 into 50 g. Sorry, 4 into 50. So this is becoming how much now? 60 minus 40 upon 60 plus 210. So that's finally coming out to be how much? 10 by 13 meters per second. You can convert it to fraction. It's okay to just leave it as this also. Okay, let's move on to the next question. This example, we come back to the inclined plane situation, but in a more complex manner. So we have this kind of an inclination where this is 37 degrees and this is a 90-degree angle. We've got a fixed pulley here. A combination of two blocks. This surface also has a coefficient of friction mu. This surface also has a coefficient of friction mu. So given that M1 is 10 kilograms, M2 is 20 kilograms. Okay, find their accelerations if the coefficient of friction is 0.2. In second case, the coefficient of friction is, so just start with the first part. 0.6. So just try this out, people. Okay, so to understand the direction of friction, first of all, you have to understand the tendency to slip. So the tendency to slip is in which direction? Here you can see it very easily, because this side the angle is also more steep and the mass of the block is also more. So this is 37 degrees. So this side is 53 degrees. So you can see that this force pulling it, m2g sine 53, is more than this side pulling it back, m1g sine 37. So since m2g sine 53 exceeds m1g sine 37, the tendency for slipping is like this. Okay. So therefore, if acceleration is non-zero, that means slipping is taking place, then the friction acting in both is kinetic friction. So that is mu into normal reaction. Okay. So in that case, our free body diagrams will look like this. On M1, there is tension M1G sine 37, M1G cos 37. Normal reaction, let's say N1, and kinetic friction, so that is mu N1. So for this one, we'll have the equation T minus M1G sine 37 minus F1 is equal to M1A. So let's substitute the values. So T minus, this will become 60, because M1 is equal to 10 kgs and theta is 37, minus friction. Now this friction, so this is 80, and the coefficient of friction given to us in the first case is 0.2. So the friction here is mu n1, so it is zero point 0.2 into 80, so 16 newtons. We have T minus 76 is equal to 10A. That's our first equation. Okay. On the other side, for this block, okay, so M2 is equal to 20 kg, mu is equal to zero point 0.2. So again, this normal reaction is equal to 120 newtons, right? And 24 newtons. Okay, so we have m2g sine 53 minus tension minus kinetic friction F2 is equal to m2a. So this will become 160, okay, minus t minus 24 is equal to 20a. So this will become 136, right? Minus t is equal to 20a. So this is our second equation. So now solving these two equations, now just add equation 1 with 2. Should be getting, okay. So that is the answer to the first part. Okay, so I'll come to the second part. First, note down the solution of the first part. Okay, now same thing you'll notice if you try to work out for some acceleration in the second case with the coefficient of friction taken as zero point 0.6, you'll get the opposite direction. You'll get A as negative. But here that is not possible. No? Friction cannot act in such a way that it causes slipping opposite to the tendency of slipping. That means what will happen? Actually, static friction will be acting, which will be less than mu n. Okay. So in the second case, if you make the same free body diagrams and you write the same equations, but you take the coefficient of friction as zero point 0.6. So for your M1, your equation is like this: T minus M1G sine 37 minus F1 is equal to M1A. And for your M2, your equation is like this: M2G sine 53 minus T minus F2 is equal to M2A. Now, if you solve these for F1 equal to kinetic friction, so mu m1 g cos 37 and f2 equal to kinetic friction, so mu m2 g cos 53. If you do that on solving, you will get something like this: t minus this was 60, okay, minus this will become zero point 0.6 into 80 na? So 48 is equal to 10a, or t minus 108 is equal to 10a. That will become our equation 1, and equation 2 will become, this was 160 minus t minus, so it will become zero point 0.6 into 120, so 72, yeah, is equal to 20a, or this will become 88 minus t is equal to 20a. So on solving this system, you will get a as a negative quantity, you can see. But you can see that in this case, a negative is not possible. Okay. So this is not possible because friction cannot cause motion opposite to slipping tendency. Okay. If there had been no friction, the tendency of slipping for the two blocks is in the opposite direction to this. So now friction cannot overcompensate and create slipping in the opposite direction. So instead we know that therefore acceleration is actually zero. The blocks will remain at rest. Okay. And F1 and F2 will be static frictions. Okay. So F1 will be less than equal to mu n1. F2 will be less than equal to mu n2. So the friction F1 acting will be less than equal to the limiting value which we had seen above here was 48 newtons, and this one was 72 newtons. Okay. Such that from this you will get that 60 plus F1 will be equal to 160 minus F2, or F1 plus F2 sum will be 100 newtons. So these will be static frictions such that their sum should be equal to 100 newtons. Whereas the maximum possible sum you can see is 48 plus 72. So that is equal to how much? That is a lot more, no? That is 120 newtons. Okay. So up to a maximum of 120 newtons of total friction is available to us, but we need a total friction of only 100 newtons to keep the system from slipping. So that is what is going to happen over here. Okay. So what we can see from this is that maximum total friction F1 plus F2 of up to 120 newtons is available, but only 100 newtons total friction is needed. So Shikhar, there cannot be negative acceleration here. That's the first thing you have to understand. Okay. The interpretation of this, that when we are solving for E from these equations and we are getting E as negative, this is not possible here. So note this down first. Too much of friction cannot act because friction will go against its job. Okay. Direction of friction is still the same, beta. Direction of friction always opposes slipping, na? तो टेंडेंसी ऑफ स्लिपिंग कैसा था? M1 के लिए टेंडेंसी ऑफ स्लिपिंग वाज अप द इंक्लाइन प्लेन ना, तो अब M1 जब रेस्ट पे है, टेंडेंसी ऑफ स्लिपिंग को ब्लॉक करेगा ना फ्रिक्शन. Still the same all this. Still friction will act like this on M2. So now come to the equations below and you will understand why that's happening. This one. And on that one, that is how these two equations are coming. Okay, so hope this question is clear to all of you. Okay, now next let's move on to a very interesting question. So now we are coming to a situation where we will look at friction between two blocks kept on top of each other. So this is typically called the two block problem. Let's say this is M1, this is M2. So we'll see many such problems. But today we'll start with the simplest one. So this is a smooth surface, whereas this is a rough surface. And given that M1 is, let us say, 5 kilograms and M2 is 15 kilograms and G is equal to 10 meters per second square, the system is initially at rest. Now at t equal to 0 onwards, a horizontal external force F acts on the lower block. So we start pushing the lower block with an external force F horizontally. Find their accelerations and the frictional force if F is equal to 60 newtons. In fact, let's take an even lesser value. Let's take F equal to 30 newtons. Second case, F equal to 75 newtons. Okay, so just take down the question and analyze the free body diagrams, then we'll discuss about this. Okay, so let us understand this problem in detail. So what you will see is that the moment we apply a force on the lower block, okay, the moment we apply a force like this on the lower block, the tendency to slip, that is slipping between the two blocks, that is such that M1 tends to slip back, that is like this, with respect to M2, and M2 tends to slip forward like this with respect to M1. So that's why the friction that will come into play will immediately be like this. There'll be a friction like this, and there'll be a friction like this. So now there are two possibilities. Okay. Case one, if there is no slipping between the two blocks, obviously the ground is smooth, so there's no question of the block M1 being at rest or M2 being at rest. Then they will have common acceleration. Both move together with common acceleration, and this friction is static friction, so it is less than equal to v1. Okay. Whereas the second case possible, slipping occurs between the two blocks. So in that case, E2 will be greater than E1. This lower block on which we are applying the force, this will slide faster compared to the upper block, because the friction acting will be kinetic friction, and that will be mu1. So first of all, we have to understand which of the two things is happening. Yeah, Sania, your answer is for the first case, that 1.5 is correct. Okay, they will have a common acceleration of 1.5. Second case, they will have different accelerations. Now let us understand one thing from the individual free body diagrams. If you look at the block M1, on this block, in the horizontal direction, there's only one force acting, and that is friction. So let's say this has an acceleration A1. Now, all these free body diagrams I'm making in inertial frame only, in ground frame. Whereas if you look at the second block, the lower one, on this, there is this combination of forces acting. normal reaction from ground and Zen. And let's say this has an acceleration E2. So for this one, for this block, notice that F is equal to M1A. And since F has to be less than equal to mu n, or F has to be less than equal to mu M1G. Okay. So put this back here and you can understand that A1 should be less than equal to mu G. That means A1 should be less than equal to 4 meters per second square. So this tells you that no matter how much force we apply on the lower block, the upper block cannot move faster than 4 meters per second square. So this tells us that the upper block cannot accelerate faster than 4 meters per second square. So this tells us something very important, that if there is no slipping, so therefore if the blocks move together without slipping, then that common acceleration A1 equal to A2 should be less than equal to 4 meters per second square. Okay. So in other words, any value of F tending to give acceleration of more than 4 meters per second square, it will cause slipping. Okay. So the point is that if we assume no slipping condition, that is A1 equal to A2 equal to A, okay, then we can make a combined free body diagram. It is moving with an acceleration A. So on that combined free body diagram, there's only one horizontal force acting, F. So F should be equal to M1 plus M2 A. So this A should be equal to F upon M1 plus M2. But recall that for A1 to be equal to A2 equal to A, this A should be less than equal to 4 meters per second square. That means F upon M1 plus M2 should be less than equal to 4. So that means our force should be less than equal to, how much was this now? This was 20 now. It was 20, was it? Yeah, 15 and 5. So we'll take another part also where F is 90 newtons. Anyway, so this now tells us that F is less than equal to 80 means no slipping. Okay. And the friction acting will be static friction. So it will be less than equal to mu n. Whereas F greater than 80, A1 will not be equal to A2. In fact, A2 will be greater than A1, and friction acting will be kinetic friction, which will be equal to mu n. So this is like a limiting condition we have got, that what is the minimum force we require to create slipping? It's 80 newtons. 80 से ज़्यादा force हुआ, it will create slipping. So now you can see that the first two cases, there is not going to be slipping. First case, F is 30 newtons. So that is, there's be no slipping. So make a combined free body diagram first of all. And from that you will get the acceleration as F upon m1 plus m2. So that will give you acceleration as, okay. And then make the individual FBD of m1. So know how much static friction is acting on it. So 7.5 newtons of static friction will be acting on it. Whereas you know that maximum friction available is mu m1g. So that is up to zero point 0.4 into 50. So up to 20 newtons is available. But only this much will be acting. Same thing for m2 also. Only that much static friction will be acting. And cross check. So this will give you the same value. Okay. Same thing will happen in the second case also. Only the values will be different. Third case is going to be the case where slipping will occur. Second case, you increase this force to 75 newtons. Okay. But still there is going to be no slipping. So combined FBD will give you that acceleration is, that common acceleration is 3.75 meters per second square. Okay. And individual FBDs, that will show you that the static friction acting is going to be so much. You can see still that static friction is less than mu n. Still we are not close to the limiting friction condition. Okay. Third case, you can see that F is 90 newtons. So there is slipping. So A2 will become greater than A1 and the friction acting will be kinetic friction. So that will be mu n. So that will be 20 newtons. So now you look at the individual free body diagrams. On M1, there is kinetic friction of 20 newtons acting, giving it an acceleration A1. So A1 will come out to be 4 meters per second square, which is the maximum possible acceleration. This can't move faster than this. Whereas the second block, M2, on that we are applying a force of 90 and there's a backward kinetic friction of 20. It has this acceleration of A2. So F minus kinetic friction be M2 A2. So this will give us 90 minus 20 is equal to 15 E2. E2 will become 70 by 15, or that no, 14 by 3. So that is free body diagram, Shikhar. Pay attention to the FBD. This free body diagram tells you everything you need. There's only one horizontal force acting on M1. So force is equal to mass into acceleration. Yeah, eventually they will lose contact now. So eventually क्या होगा? M1 will fall down. So what will happen is it starts off like this. Both of them are moving. After some time, it's here. This is here, and then this falls off because this one is moving faster. But till it slips off, this will be their accelerations. So you can imagine this. No? You kept one book on top of the other, and you are now applying a very large force on the lower one. So it's slipping. So even if the table is frictionless or nearly frictionless. Okay, so people hope this question is clear to all of you. Okay, so make sure you revise through today's questions very carefully and then start working out H.C. Verma's friction chapter. You can attempt all questions of friction now, so you can have a sort of target of attempting most of the questions of H.C. Verma's friction chapter before next week, because then we'll be discussing some of the H.C. Verma questions in class also, along with the module questions. So that's it for today. Okay, all the best, people.